right, welcome back. So we are continuing in our function notation and analogies and whatnot. So the next step is to look at function notation because it is pretty important and useful that you understand how it works. So let's just take a look at the specific example. We have y equals square root of 2x minus 1, and it's going to describe y as a function of x. And we can verify that by making sure it satisfies those criteria for being a function. And we're going to call this function f. Now, the notation we're going to want to use is going to be revolved around f. But the first thing is making sure we understand how we have our independent variable or our input that generates our output, our dependent variable. So in this case, our input, which is our independent variable, so that's going to be x, so that's something we're plugging in. And then what we get out of it should be predetermined by the equation, or if you want to consider it some sort of machine that will transform it, that's another way to think of it. So your input x is going to undergo a series of transformations dictated by f. And so what are those transformations? That would be this square root stuff. So the number one question that you might have would be, why even do this? Why do we need function notation? And truthfully, the answer is simplicity. It's much, much simpler to reference a singular equation when you have a bunch of them that you're dealing with. So, if you had, okay, y equals this, y equals something else, y equals a third option, how do you know which one you're working with at any given time? But by giving them a name, so this is function f, we could have function g or, t, whatever we want. But by giving it a name like that, it's easier for reference, and it's easier for looking at how the input and the output tie to one another. And let me give you an example. So if we use our regular notation here, y equals the square root of 2x minus 1, we'd say, okay, let's say what happens when x is equal to 1. When x is equal to 1, we can substitute that in to our y formula. And we can see we get the square root of 2 minus 1, which is the square root of 1, which equals 1. So in this sense, we have two equations that are describing the process for this equation. But if we look at it in terms of a function, I have f of x equal to the square root of 2x minus 1. If I wanted to have an input of x equal to 1, all I do is replace that in this original notation on the left. So I would say f of 1 is equal to, and now I do the same thing. I substitute in 1 in for x, and then I would simplify it down, and we get the same answer. So from this, I get f of 1 equals 1. One equation, one statement tells me two things. It tells me what my input is, and it tells me what my output is, just in this one statement. I don't have that same sort of situation going on over here. I have to have one equation telling me the input and one equation telling me the output. It's harder to tie those two things together in this format. This format is much, much clearer. That's my input, that's my output in this specific function f. But if you're working with multiple equations, that's why it's important to give them all their own name. So let's take a look at the next examples. We have one function f, which is 2x minus 3. We have another function h with a variable of t, and it's dictated by t squared minus 2t. So now, if we're working with both of these simultaneously, how do we know which one we're working with? It's all in the names. This one wants you to work with f, and it wants to know what happens when you plug in 1 for the input. Well, we can do that. Substitute 1 in for x, and then simplify it down, and boom, -1, done. What about f of a? Well, it seems kind of weird, but they want you to substitute a in for x. Anywhere there's an x in the equation, in the function, you replace it with an a. So we would get 2 times a minus 3, and you're done. Now, where this gets a little trickier is when you have to substitute an expression in. Not just a variable, but an expression in as your input. So you gotta be really careful how you do this. A lot of students do this incorrectly. So, in this case, do we simply write 2x minus 3 and then just subtract the 1 at the end, because that's what that -1 says, right? That's a big no-no. This would not be correct. This wants you to replace the variable in the function with x minus 1. This has to replace the x in both of these locations. So you would say f of x minus 1 equals 2 times x minus 1, and then you still got that minus 3 at the end. That would be the proper substitution for this. And now you're just going to simplify it. So we can distribute and then combine like terms, and we're done. So 2x minus 5. So really want to be careful with this. This is a very important concept to understand and to apply correctly. So we're going to see that a few more times. Let's work with h now. So now we're working with h. We want to replace the input with 2. So wherever there's a t, we replace it with a 2. So 2 squared minus 2 times 2. And now we can quickly do that. Follow the order of operations, and we get 0. Now we got a fun one. So now we want to replace our input with x plus 2. Everywhere there's a t, we need to replace it with an x plus 2. So h of x plus 2 should equal, so we want t squared. So the t is being replaced with x plus 2. So let's put it in parentheses and square it. But then we got to subtract 2 times our new input. So that's the proper way to substitute it. And again, we got to simplify it. So we hopefully can FOIL this out in our heads. First, outside, inside, last. So we should get an x squared plus 2x plus another 2x. So that's going to be a 4x. And then we're going to have the plus 4. And then we want to be careful when we distribute that -2 in there. So minus 2x minus 4. And go a little bit further. We can combine like terms. 4's are going to cancel. The x's will combine. So it looks like x squared plus 2x. And done. So that's some basic substitution in a singular function. Now remember, we also have piecewise functions that looks differently on different parts of the domain. So how does this process work for those types of functions? Well, we have an example here, 2x plus 1 for x less than 0, and then 2x plus 2 for x greater than or equal to 0. So again, wherever that input is, we have to make sure we apply the right path to answering the question. So in this case, if we wanted to know what f of -1 is, do we just substitute it into both paths and write both answers? No, because this input only satisfies one of these two restrictions. So the -1 will satisfy the first restriction and not the second one. So that means it only goes in that first pathway. So we would want to say 2 times -1 plus 1. So -2 plus 1 is -1. And that's it. There's one y value for this particular piecewise function. If we wanted to have an input of 0, where do we plug it? Top or bottom? If you said bottom, you are correct, because it satisfies this inequality. 0 is greater than or equal to 0. So substitute that in. So plus 2 now. 0 plus 2 is 2. So what about f of 2? What should f of 2 be then? So again, top or bottom, and then just simplify it down. And hopefully you said bottom. So 2 times 2 plus 2, 4 plus 2 is 6. All right. And so now this last one. So now we have an expression to plug in to a piecewise function. Well, we still want to know what pathway we're plugging it into. Are we going to end up with another piecewise function or not? It really depends on that input. What does that input tell you? X squared plus 0, or excuse me, x squared plus 1. What do we know about that? If you plugged in a value of x, what's that going to do to it? Doesn't matter what we plug in. If it's a positive or a negative number, when we plug that in, it's going to get squared, which makes it positive. And then we're going to have to add 1 to it, which still makes it positive. So we're always going to have a positive number for this input no matter what value of x we pick. So which pathway should we take? If our input is always going to be positive, it forces us to take this bottom pathway only. The input will never be negative. So we can't use that top pathway. So we're not going to end up with a piecewise function. We'll end up with a singular function. So in this case, we want to plug in x squared plus 1 into the bottom pathway only. And now simplify. So distribute and then combine like terms. So 2x squared plus 4 should be our answer for that one. All right, so we're going to stop there, and then we will continue more applications of this in the next video. See you soon.